In this video, I'm going to explain how filtration occurs at the glomerulus and Bowman's capsule of the kidney. So the Bowman's capsule is the first part of the nephron where the filtrate actually forms. So this structure right here is the Bowman's capsule. And the Bowman's capsule leads to the next part of the nephron, which is the proximal convoluted tubule. So these cells here are the first cells of the proximal convoluted tubule, or the PCT. So these are part of the nephron itself. The Bowman's capsule also has associated with it these cells called podocytes, which surround or kind of engulf, in a way, the capillaries of the glomerulus. So within these podocytes are capillaries which contain blood. So entering these glomerular capillaries is blood, which comes from this afferent arteriole, which we'll label in a minute. So in here are the blood capillaries surrounded by these podocyte cells. Infiltration happens when fluid from the blood here is squeezed into this Bowman's capsule through these filtration slits. So let's show the filtrate that forms, and we'll put the filtrate in the Bowman's capsule. We'll make the filtrate yellow since urine is typically a yellow color. It's not really urine yet, we just call it a filtrate so far, that's squeezed from the blood that came from these capillaries, which are engulfed by these podocytes. So let's label one other thing on here, in one more part of the nephron, and this is the distal convoluted tubule, and this has filtrate in it as well. I guess we probably could color some filtrate in there. So the distal tubule is one of the later parts of the nephron. However, the way the kidneys folded up on itself in the nephron, it ends up being in very close proximity to this afferent arteriole. Okay, well, let's go ahead and label the blood supply. So I'm going to actually start all the way over here with the heart, which generates hydrostatic pressure. And I'm going to abbreviate hydrostatic pressure as HP, since we've talked about that before when we talked about formation of lymphatic fluid. So the heart generates hydrostatic pressure, and it pumps blood into the aorta, since we're talking about the systemic circulation. And the aorta leads to the renal artery. And the renal artery then leads to this afferent arteriole, which we've been talking about. So you can put afferent, the A on afferent, with arrive, and the blood arrives from the afferent arteriole and then moves into these glomerular capillaries. Fluid is squeezed out into this Bowman's capsule, where we call it filtrate, as it then will move through the nephron. Well, only about 20% of the blood that enters the glomerular capillaries gets filtered. The other 80% leaves the capillaries and moves into, we should put some blood entering here, moves into the efferent arteriole. So this is the efferent arteriole. So the efferent arteriole exits the capillaries. And the efferent arteriole then leads to another capillary bed that are called the peritubular capillaries. That's a U for peritubular capillaries. These capillaries are draped all over the nephron, and when fluid and nutrients and ions are reabsorbed from this filtrate back into the blood again, it's picked up by these peritubular capillaries. And these glomerular capillaries, in line with the peritubular capillaries, are referred to as the renal portal system. So these capillaries converge onto some venules and veins, and eventually back to the vena cava and back to the heart again. So to give you an idea of the overall circulation that's happening here. Okay, so this is just like formation of lymphatic fluid, the same kind of principle. We've got, except we have one other pressure to worry about. The first pressure that we're going to talk about is the hydrostatic pressure. So remember, that's generated by the heart, and that causes fluid to be squeezed out of these glomerular capillaries into the Bowman's capsule. And typically, the pressure of squeezing out is about 55 millimeters of mercury of hydrostatic pressure. And this filtration apparatus formed by these slits between the podocytes and the junctions between the endothelial cells of the capillaries, and also a meshwork called the basal lamina of proteins and carbohydrates, forms a molecular sieve, and that makes sure that proteins, especially larger ones, a few small proteins and fragments of proteins get out, but basically proteins and cells stay in the blood, and only fluid and ions, water and ions and nutrients and fragments of proteins and only very small molecules get squeezed out into this filtrate. Well, and so because the proteins are staying in, then we also, like when we have formation of lymphatic fluid, we have colloid pressure pulling fluid back into the blood again. And that is a pretty significant pressure. We have about 30 millimeters of mercury of colloid pressure, which pulls fluid back, and largely due to the proteins in here. There's one other pressure we have to worry about that we don't when we're forming lymphatic fluid, and that's a pressure called back pressure, and it's kind of a physical thing. This is really a pretty small space in here, and so when fluid is squeezed out, it's kind of pushed back from the walls of the Bowman's capsule, and so we have about 15 millimeters of mercury of back pressure. And I'll just write back P. So we can look at these three pressures and say, okay, who wins the epic battle between squeezing fluid out and pulling fluid back in? And we say that the net filtration pressure is 55 minus 30, pulling back, minus 15 of back pressure, and we end up with a net filtration pressure of 10 millimeters of mercury out. And this converts to what we call a glomerular filtration rate, or GFR, of 115 mils per minute. And that's a pretty typical rate to filter blood in your kidneys. If you don't have any major disturbances to homeostasis where you have to get rid of extra fluid or conserve fluid, then you will go along filtering at a rate of 115 mils per minute. Well, what affects this rate? Well, the back pressure and colloid pressure are nearly constant. So back pressure, colloid pressure, I'm going to put constant. The only time your colloid pressure would change would be similar to when we were talking about formation of lymphatic fluid. If you've got a problem with your liver and you're not making plasma proteins, or if you had damage to these capillaries and you lost the protein concentration gradient between the blood and the filtrate, then you would lose some of that colloid pressure and your GFR would increase. But under normal conditions, the back pressure and the colloid pressure don't change. So the only thing that can change then is the hydrostatic pressure, and that is determined by the state of contraction of this afferent arteriole. Notice it has some smooth muscle on it. And the smooth muscle can contract to reduce the amount of blood that enters this glomerular capillary, and so that will reduce the glomerular filtration rate by reducing the hydrostatic pressure. Or if this muscle relaxes, it will let more blood in, and you will have higher pressure in this small space, and you will squeeze more fluid out. So what affects the state of contraction of this smooth muscle? That would be our vasodilators and our vasoconstrictors. So now you need to go to your notes and look at all of the different factors that can result in cause a change in the state of contraction of the smooth muscle of this afferent arteriole, thus influencing the glomerular filtration rate and whether you get rid of excess fluid or conserve excess fluid.